I'll be presenting on relativistic dynamics, and in particular on the difference between the classical and the relativistic predictions. So classical mechanics starts off with the assumption of Euclidean flat space and time, that space and time are both absolute. Some relations that it has is that momentum is just the product of mass and velocity, and that kinetic energy is p squared over 2m. Relativistic dynamics assumes, or is most natural in Minkowski spacetime. Both space and time are relative. You don't have any privileged reference frame. You don't have any privileged origin. You don't have any privileged velocity. And there's a universal speed limit of the speed of light. Nothing can go faster than the speed of light, according to relativistic dynamics. The relations of relativistic dynamics have that P equals gamma mv, with gamma, as Thomas said, 1 over the square root of 1 minus beta squared, where beta is v over c. Kinetic energy is then gamma minus 1 times mc squared, and total energy is gamma mc squared. We decided to test relativity. Why do we care? So my answer is because relativity is awesome. There's also other answers that if you want to understand things that are moving really quickly, you need relativity. If you want to understand how light works and how things moving near the speed of light work, you need relativity. If you want to understand the lifetime or the decay of particles moving near the speed of light, you need special relativity. If you want to understand GPS, you'll need general relativity. So you need relativity in a lot of things. So how do we test relativity? Well, we move really, really quickly. What moves really quickly? Well, first thing that comes to mind is light. So light moves really quickly. Well, it's not particularly easy to do experiments with bending light or keeping light confined in some small area. So that's not going to work very well. So electrons can also move really fast when they have high energy. They're not very massive, so it's easier to get them moving quickly with reasonable energies. So we used strontium ytterbium-90 as our source of electrons. They're both primarily beta emitters. They do emit, I think, antineutrinos. I believe most of the energy goes to the electrons, though. This is the decay process. So there's two ways that we tested relativity. You can test it using force and momentum, or you can test it using total energy and momentum. I'm going to talk primarily about force and momentum. So if a particle is traveling in circular motion with radius r, then F, which is always equal to the time derivative of momentum, is equal to mv squared over r times gamma. And if it's an electron or any charged particle traveling through a uniform magnetic field, with a little bit of manipulation, you see that momentum is equal to the charge of the particle times radius across the magnetic field. And so first I'll cover the apparatus and then go back to the formulas. So again, as Thomas said, we have a radioactive source over here. It emits electrons. We have a uniform magnetic field throughout the entire vacuum chamber. A uniform magnetic field causes charged particles that are moving in the plane perpendicular to it to go in circular paths. The radius of the path depends on the speed at which the particles are going. The wall over here blocks off anything that's going too slowly, which will have a large radius. It also blocks off anything that's going too quickly, which will have a small radius. And then we select even more when they get over here to the velocity selector. The velocity selector for one particular speed will cancel out the magnetic field, and so that speed will just go straight into the pin diode, and anything that's going faster than that so the speeds around that, some of them will still make it to the pin diode. If something is going too slowly, then the electric field will send it into one of the walls and it won't get to the pin diode. If it's going too quickly, the magnetic field will send it into one of the walls and it won't get to the pin diode. So the velocity selector again selects on both sides. And then the pin diode, when it's hit with ionizing radiation, there's a signal that comes out of it. It goes through our circuitry and we get a signal after amplification. So we can measure when electrons hit the pin diode. So in the velocity selector, for approximately the middle velocities, the ones that we're particularly interested in, we have the total force equals 0. Those are the ones that are just going to go straight once they get into the pin diode. And for that, because of the relativistic formula, here I'm using SI units, you get that E times the charge of the particle times the electric field is equal to the charge of the particle times the velocity times the magnetic field. You can rearrange this to find that E over B equals V, or E over CV equals beta, again in SI units. And then you combine our relation from before with this relation, and you get that, you get that E over B, that over V is equal to V over C over momentum over momentum over the charge times the radius. If you use the classical prediction for momentum, then you get that this quantity is equal to charge times radius over mass times the speed of light. This is just a constant, so we should see a straight line. The relativistic prediction says that that momentum is equal to gamma times mv. This gives us the same coefficient out front, but now we have a square root of 1 minus beta squared. That's velocity dependent, and so we should see a curve. So what do we get when we do this? This is the classical prediction with appropriate error bars from the measurement of the radius of the device. This is the relativistic prediction with error bars from the same thing. And this is the data that we measured. If you zoom in on it, you see this. And the horizontal error bars come from our estimate of the B field varies by about 2 Gauss. The vertical errors come from a combination of the error in the distance in the velocity selector, the error in the radius, the error in the B field, the error in finding the center of the peaks in the B field, and the uncertainty in the E field on the voltmeter that we read. And you notice that they they look like they curve decently well with the relativistic curve, but there's a systematic error that they're off by. So if you do the math on how far you have to change these things, if you change voltage by 0.2 kilovolts, that will set them so that the center lies right on the relativistic curve. It gives you a forfeit, though. It still doesn't line up with the curve perfectly. The left side is, I think, low and the right side is high. It's possible that the point graph equals 0 is not exactly the center of the peak, which is what I assumed. So because the peaks, we saw that they're about half a kilovolt to a kilovolt wide, it's reasonable that it's biased towards one side or the other, and that our center measurement is off by something like 0.2 kilovolts. The distance between the plates of the velocity selector was given as 0.183 plus or minus 0.003 centimeters. If it's systematically high by 0.01 centimeters, then it gives us a beautiful fit, but it's 3 sigma. This is the fit that I got just by dragging it by that amount. I didn't figure out what the perfect amount is, but this fit looks remarkably good for 0.01 centimeters off. The Gauss meter could be systematically high by 5 Gauss. Again, it's a poor fit. You get the same lopsided distribution. We found a 2 Gauss variation along the track, so 5 Gauss is not completely insane. And finally, the measurement of the radius could be high by about 5 centimeters. Again, it's a poor fit, and this is 20 sigma off, so I think that this is particularly unlikely. So the best fit, I think, is given by changing the distance between the plates. It's possible that it's some combination. It's entirely feasible that the velocity selector isn't symmetric in how it deals with things that are going too quickly and things that are going too slowly, and so that contributes some significant portion of it. Maybe it's something else entirely. But regardless, the conclusion is that relativity wins. The data fits the relativistic curve much better than it fits the classical curve. Thank you. Any questions?